Welcome to the Unit 10 Section 2 video on factoring techniques. You have learned many different methods for factoring. The table below lists the methods you have learned, the definition for each method, and when to use them. So let's summarize each method that we have learned. Using the greatest common factor is the first method you should always go to. This can be used with any polynomial. See what you can factor out first, and then see if it can be factored further. Difference of squares only works when you have binomials, when both terms are perfect squares and the operation being performed is subtraction. A perfect square trinomial, you're going to be looking for a perfect square for the last and first terms, and the middle term being 2 times the square roots of your first and last terms. A trinomial with a equals 1, you're going to be using that with trinomials. The leading coefficient must be 1, and to be factored, there must be 2 numbers that multiply to c and add to b. The AC method is used when you have trinomials with a leading coefficient greater than 1. To be factored, there must be 2 numbers that multiply to AC and add to b. And because we're looking for 2 numbers that multiply to AC, this is why it's also referred to as the AC method. And then factoring by grouping, you're going to be looking for polynomials with 4 or more terms, and factoring out a greatest common factor in each group of terms should leave a term common to each group. So you want to recognize common patterns, such as a polynomial with 4 terms would typically point to factoring by grouping. A binomial would typically point to a difference of squares. A trinomial with perfect squares for the first and last terms would typically point to a perfect square trinomial, and a trinomial with a leading coefficient greater than 1 would point toward the AC method. If none of the factoring methods work, the polynomial is unfactorable. So let's take a look at a few different examples and see which factoring technique will work for each. So this one is a trinomial. We have a perfect square for the first term, but the last term is not a perfect square. So this is not going to be a perfect square trinomial. The leading coefficient is 1, so we're going to factor this using a traditional method of finding the factors of negative 40 that add to give us 3. So we go through negative 1 and 40, that gives us 39. That's not going to work. Negative 2 and 20, add to give us 18. That doesn't work. Negative 4 and 10 gives us 6. That doesn't work. Negative 5 and 8 is 3. That is our middle term, so that works. So this can be factored into n minus 5 times n plus 8. For this one, we do not have perfect squares for the first term. We do for the last term, but not for the first term, so we can't use a perfect square trinomial here. We do have a leading coefficient greater than 1, so we are going to use the AC method. So 6 times negative 9 is negative 54, so we want factors of negative 54 that add to negative 25. And it doesn't take long to find that those factors are 2 and negative 27. So we're going to split up that middle term into 2x and negative 27x, and then we'll factor by grouping, getting our common term for both being 3x plus 1, leaving behind the 2x minus 9. Here we have 4 terms. So 4 terms should immediately key you in to looking at factoring by grouping. So we're going to group the first 2 terms and the last 2 terms and factor out our greatest common factor in each set, which leaves behind a b plus 5 in each. And when we factor the b plus 5 out, that leaves 5b squared minus 4. Now that is almost a difference of squares there, but not quite, because 5 being the coefficient of that first term is not a perfect square. So this is as good as it gets when we factor this one. All right, let's check out the next one. We've got 4r squared minus 9. It's a binomial. Both are perfect squares, and it's a difference of squares, so we are going to use that and end up with 2r plus 3 times 2r minus 3. 12x plus 4 is a binomial, but they are not perfect squares. But we do have a common factor that we can pull out, which is 4. So we have 4 times 3x plus 1. And then finally for f, we have a trinomial. That trinomial is a perfect square trinomial because the first term is a perfect square, the last term is a perfect square, and the middle term is 2 times the square root of the first and last terms. So we have 2x minus 1 quantity squared. Recall that a polynomial is in its fully factored form when it is written as a product that cannot be factored further. To factor a polynomial completely, you may need to use more than one factoring method. Use the steps below to factor a polynomial completely. So the first thing you should do is check for a greatest common factor. Remember to carry it through the entire problem. Okay, it's going to be sitting on the outside, but remember, you need to carry whatever term you factor out all the way down to your final answer. Second thing, check for a pattern that fits the difference of two squares or a perfect square trinomial. To factor x squared plus bx plus c, look for two numbers whose sum is b and whose product is c. To factor ax squared plus bx plus c, look for two numbers whose sum is b and whose product is ac. And then check for common factors. So let's factor each polynomial completely. And when we say completely, it means no piece can be factored any further. So in example A here, first thing we're going to do is look for a greatest common factor that can be factored out of the entire trinomial. And number-wise, we have -2, and variable-wise, we can pull out an x. And that's going to leave us with the trinomial y squared minus 8y plus 16. So now let's factor that trinomial by looking for two numbers that multiply to give us 16 and add to give us -8. Alternatively, let's see if it's a perfect square trinomial. The first term is a perfect square. The last term is a perfect square. And if we take the square root of both and multiply them together, we get 4y, and double it, you get 8y, which is your middle term. So actually, we can bypass the first process and just go straight to y minus 4 quantity squared. And remember to keep your -2x on the outside from when you factored out your greatest common factor. All right, for the next one, we have a trinomial. It looks like we can pull out an n squared. It looks like we can also pull out a 3. So we'll pull out a 3n squared. That leaves n squared minus 5n plus 4. We want two numbers that multiply to give us 4 and add to give us -5. And -1 and -4 would meet that requirement. And that is our fully factored form. 3n squared times n minus 1 times n minus 4. For this trinomial, we can pull out an x. We can also pull out a 2 because all of those coefficients are even numbers. So we'll pull out a 2x. That leaves 2x squared plus 9x plus 10. And then we will see about using the AC method. Two numbers that multiply to give us 20 and add to give us 9 are 5 and 4. So we'll split up that middle term into 5x plus 4x and factor by grouping. We get a 2x plus 5 in both of those terms, so we'll factor that out, leaving behind an x plus 2. P to the 5th minus p, we can factor a p out. That leaves p to the 4th minus 1, which is a difference of squares. So we have p squared plus 1 times p squared minus 1, but p squared minus 1 is also a difference of squares. So we end up breaking that up into p plus 1 times p minus 1. So we finally end up with p times p squared plus 1 times p plus 1 times p minus 1. To write expressions for the length and width of a rectangle whose area is expressed as a polynomial, you need to write the polynomial as a product. You can write a polynomial as a product by factoring it. So for this example, Mandy's calculator is powered by solar energy. The area of the solar panel is 7x squared plus x centimeters squared. We're going to factor this polynomial to find the possible expressions for the dimensions of the solar panel. So we take our area, 7x squared plus x, and we're going to factor it by pulling the x out, and that leaves us with 7x plus 1. So possible expressions for the dimensions of the solar panel are x centimeters and 7x plus 1 centimeters. That is our length times width. A farmer has partitioned his field into rectangular areas. One section of the field has an area of x squared plus 13x plus 42 square miles. Factor this polynomial to find possible expressions for the dimensions of the field. So we're going to take our area and we're going to factor it. We need two numbers that multiply to give us 42 and add to give us 13, which would be 6 and 7. So possible dimensions for the field are x plus 6 miles and x plus 7 miles. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you. And if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.